You are welcome to the GMAT 41's Ordinary Differential Equation class. In this video, we are going to look at the second order ordinary differential equation, O.D.E. You will recall that in previous classes we've treated O.D.E, first order ordinary differential equation, for which of course we encounter different types of it and we apply the method that is peculiar to a particular type of first order ordinary differential equation and obtain the solution of that first order differential equation. Now we want to move on to a second order ordinary differential equation, which is one in which the dependent variable, because in most cases we use y to represent it, dependent variable, have been differentiated twice with respect to the independent variable, which in most cases you see as x. The dependent variable, which is y, that has been differentiated twice, is written in this order. You can see that d2y d squared x. So this shows that the dependent variable y has been differentiated two times with respect to the independent variable x. Generally, a second order ordinary differential equation is given by what we have on the board here. A d2y d squared x plus b dy dx plus cy equal to f of x. This is the general representation of second order ordinary differential equation, O.D.E. Now, we have types of second order O.D.E. A second order ordinary differential equation could be homogeneous O.D.E. or it could be non-homogeneous O.D.E. It is homogeneous when this f of x is equal to 0, and then the equation will look like this. You can see a d2y d squared x plus b dy dx plus cy equal to 0. You notice here that in this part where you have cy, this y is the variable. It was not differentiated at this point. Coming here, this is the first derivative because it's bearing its coefficient b, and then this is the second derivative of the dependent variable y, bearing the coefficient a. So when it is equal to 0, we refer to it as the homogeneous second order ordinary differential equation. What if f of x is not equal to 0? It's not equal to 0. What if it is just some kind of function, alright? It could be a constant, which is not 0. Something like 1, 5, minus 3, It could be a function of x itself, okay? Maybe say a polynomial function. It could be a trigonometric function. It could be an exponential function. So in the case where f of x is not equal to 0, then we refer to that O.D.E as a non-homogeneous O.D.E. Second order ordinary differential equation, non-homogeneous. We are going to deal with the homogeneous second order ordinary differential equation in this class. So, come along with me, let us look at the concept of homogeneous O.D.E. Already we've stated that the second order ordinary differential equation is written in this form, is that so? And how do we obtain the solution of a second order ordinary differential equation, the homogeneous type? It might interest you that this simply depends on your ability to solve a quadratic equation. Usually we can think of using factorization method if that quadratic equation generated from this O.D.E can be factorized. Or we can think of using the completing the square method, alright, if the quadratic equation obtained from this O.D.E cannot be factorized. So what are we trying to say in essence here? To get the solution of a homogeneous second order ordinary differential equation, the solution is also known as complementary function. To obtain it actually depends on the solution of the quadratic equation you're going to obtain from that homogeneous O.D.E. The quadratic equation is known as auxiliary equation. Look at it. This auxiliary equation is obtained from here. A, which is the coefficient of the second order derivative of y. This n passively represents the derivative. Are you following? Now you can see raised to power 2 telling you the 2. And then plus b, look at the b, times m raised to power 1. Power 1 because this is first order derivative. Then plus c. This term is not bearing any derivative, you know that, right? So even if you fix m here, we could say m raised to power 0, which will still give you 1, you know that, right? And 1 times c. So in this part, at this point you just pick your c there, which is a constant, and you make it equal to 0. This is known as the auxiliary equation. Of course, you see it is a quadratic equation. So when you solve this quadratic equation, you obtain what we call the root of the equation. You know about that, right? And of course, the root of the equation will now determine the solution of the homogeneous O.D.E that is given to you. 5 different types of solution have been identified for a problem involving homogeneous O.D.E. In the next video, we're going to see these types of solution, which are dependent on the root of the auxiliary equation that you obtain from that homogeneous O.D.E. In this video, we now want to look at the complementary function. That's the solution to homogeneous O.D.E. You will recall that in the previous video, I stated that the solution depends on the type of root of the auxiliary equation you obtain. Is that not so? So when you solve the quadratic equation, the root of the equation you're going to get there will determine the solution of that homogeneous O.D.E. And that's why on the board here we've got 5 solutions that you have to get to know about. Although these equations are these complementary functions, otherwise known as solutions, 1, 2, 3, 4, 5, are derived. Alright? However, we've chosen to just pick these solutions. When problems are given to you, all you need to do is solve the auxiliary equation for that homogeneous O.D.E. and then pick the solution that applies to it from here. Fix in the value of the root of that auxiliary equation you obtained, and that's all. Is that okay? So we've written these equations or these solutions on the board without derivation. When problems are given to you, you don't really bother yourself deriving them. Is that okay? Go straight ahead and solve the homogeneous O.D.E. and then pick the solution that applies it. Now, how do we know the solution that applies to a particular root, particular zeros of the quadratic equation, of the auxiliary equation that we obtained? You solve a problem, you get rid of the auxiliary equation. How would you know the solution that applies to it here? That's what we now want to learn. Are you ready? Alright, fellow land, let us look at the first solution here. Now, when the auxiliary equation is of this form, an squared plus bn plus c equal to 0, you can take it. That is to say that it contains possibly all the 3 terms. All the 3 terms, or let's say the first order derivative term and the second order derivative term. That is in the case of this first solution anyway. But let's look at it generally. If this is the auxiliary equation, so it contains the 3 terms in quadratic equation, that's the square term, the raised to power 1 term, and the constant term. And then you solve that quadratic equation, that's the auxiliary equation. You're going to get the root of the equation m1, m2. Now, if m1 and m2 are real numbers, and their values are not equal, that is to say that m1 and m2 have different values, the solution that applies to that is this solution. So what do? Once you get the value of m1 and m2 from this auxiliary equation, simply copy this solution and substitute for what? m1 and m2. A and B are the constants of integration which can be obtained for a given IVP situation, that is initial value problem situation. Is that okay? Alright, take note. For us to use this solution, it means that this auxiliary equation must be factorizable. Please put that down because I didn't write it on the board here. This solution applies when the auxiliary equation is a factorizable quadratic equation such that the roots of the equation m1 and m2 are real numbers and they are not equal. Let's move on to the second solution. This, where we have y equal to a plus bx times exponential mx. Of course, you can still write it as ax plus b. It's not compulsory that it is b that must bear x. No, a can also bear it, so it can be of this form. Ax plus b in bracket times exponential mx. When do you use this complementary function, this solution? You use it if on solving this auxiliary equation you obtain real roots. That is, the roots of the equation are real numbers and they are equal. That is to say m1 is equal to m2. In that case, you can simply use m to represent it. I follow it. Let's represent the root of the equation. Hence, this is the solution that goes for it. All you need to do is to copy this solution and then substitute for n, which is the root you obtain from solving this auxiliary equation. I hope you're following. Once again, this solution is used when the quadratic equation, that's the auxiliary equation here, is factorizable. Put this down as well too. Alright, this second solution is also used when the auxiliary equation is factorizable. And of course, you get the root of the equation to be real numbers such that the roots m1 and m2 are the same. Let us now move on to the third solution. Alright, this solution is actually used when the auxiliary equation cannot be factorized. In that case, you'll be thinking of using the completing the square method, or of course, you can use the quadratic formula. Is that okay? Put that down. This solution comes in when the auxiliary equation cannot be factorized. In that case, you either use completing the square method or you can use the quadratic formula. And in what case do we use this solution number 3, this complementary function? It happens when m1 and m2, that's the root of the equation, are imaginary roots. Is that okay? You know what we refer to as imaginary number, right? Good. Usually the discriminant part of the quadratic formula, that part that has square root of b squared minus 4ac, that part will give you a negative number inside the square root. And once you have that negative number, of course, you know you're going to get imaginary roots. They wouldn't be real numbers as your root. Are you following? You get imaginary root. And generally, the root of the equation is given as this: m equal to alpha plus minus I beta. This alpha is the real part of the root. Are you following, right? And then this IB is the imaginary part. Of course, you know in the study of complex numbers, z equal to x plus iy. A complex number which is imaginary contains a real part and what? An imaginary part. The fact that there is an imaginary part makes the whole thing a complex number. Is that okay? So in a situation like that, you know that what you're going to use as the complementary solution of function is this equation 3. This and this are the same thing. Is that okay? I just wrote them in these two forms to tell you that any one of them could carry a constant of integration there, a or b. Is that okay? Now on solving this, you will get a solution that looks like this: alpha plus minus I beta. So substitute for alpha here and substitute for beta. Is that okay? And that will be the solution. Now let us look at the complementary function number 4 type. Is that okay? These solutions are used in a case where b is equal to 0. Of course, you know if b is equal to 0, this term will reduce to just 2 terms: am squared plus c. Of course, this could also be minus, you know that. We have plus here. It doesn't mean that when questions are given, all you're going to see there is plus. You can see minus as well too. And that is why in this case I've decided to use plus or minus. So equal to 0. How do we handle that? All you need to do is divide through by the coefficient of m squared. If you do that, this is what you're going to get. Are you following? And then if we call c over a, if we represent it with n squared, you notice that the auxiliary equation will now be m squared plus n squared equal to 0. If you solve this auxiliary equation to get the value of n, which is the root of the equation, this is what you're going to get. Are you following? Because if this n squared goes over there, it will become minus n squared on the right hand side. To get n now, you'll be taking square root of minus n squared. And you know that square root of a negative number, just like I explained regarding the discriminant part, square root b squared minus 4ac of our quadratic formula, right? The almighty formula, some persons call it that way. If you do that, as long as you're enclosing a negative term with square roots, you're going to get an imaginary number. And that is the concept of this imaginary here, I. So you're going to get in as a solution of that problem. That I represents imaginary, just like you have it in this case. When that happens, the solution to that differential equation, second order, are you following, right? Is going to be a cos nx plus b sine nx. Take note of this one, this exponential alpha x. A cos beta x plus b sine beta x. Or you could still write it as a sine beta x plus b cos beta x. This solution 4 was actually obtained from solution 3. Take notes. The only thing that happened here is that this solution 4, the root of the equation does not have a real part. It doesn't have the alpha part. Are you getting? No alpha. So if there is no alpha, it means that alpha is 0 here. If you fix in 0, exponential 0 times x will give you 1. So 1 times this bracket maintains that bracket for you. Now the last of the solution you need to know is when you're dealing with am squared minus cy equal to 0. You can see that. So I've quickly divided through by a to have it like this. Then c over a, if we call it n squared, pick out the auxiliary equation and solve. The auxiliary equation will be m squared minus n squared equal to 0. If this minus n squared goes over there, it will be plus n squared. And then you take square root of both sides. Square root of a positive number will still give you positive, not negative, so there's nothing like imaginary number there. Is that okay? And once you're done with that, you now have that n is equal to n. So n will now be the root of that equation as the solution of n. If you do that, the complementary function, the solution to the homogeneous O.D.E of this type is given by this equation 5. Y is equal to a cos nx plus b sine nx. Don't forget, you can actually also write it as a sine nx plus b cos nx. This is a hyperbolic solution. Is that okay? Hyperbolic function solution. So that is all about the complementary function, the solution to a homogeneous O.D.E. In the next video, we're going to pick questions to solve and see how we apply these solutions that have been written on the board. It is now time we want to pick questions and solve. We've got this first question on the board. Okay, this question is a homogeneous O.D.E. We are required to find the general solution of the equation y prime prime plus 3y prime plus 2y equal to 0. Because you know the prime prime concept in prime represents second order derivative of y and then first order derivative of y. There are other forms in which we can express the concept of d dx. Is that okay? Sometimes you can say it as capital letter D. We'll use all those different formats as we move in solving question. Let's quickly digest this problem on the board. It's a simple one. How do we solve that? At the end of what you're going to see me do here, please test your zone of proximal development by obtaining the complementary function of the differential equation giving us y prime prime plus 7y prime plus 6y equals 0. Remember, complementary function is also the same as getting the solution of a given homogeneous O.D.E. Let's do this. The question given to us and to solve is y prime prime plus 3y prime plus 2y equal to 0. Told you this means the 2y d squared x plus 3 dy dx plus 2y equal to 0. Now let us pick the auxiliary equation out. Is that okay? Let us pick out the auxiliary equation. Now auxiliary equation is given as auxiliary equation to this dE is given as n to power 2. So n squared plus the coefficient here is 3. So it's going to be 3 times n to power 1, which is simply n. Then plus you pick this coefficient here 2, and that will be equal to 0. So this is the auxiliary equation, which is a quadratic equation. We shall solve this quadratic equation and see. But first of all, let's check. Can we factorize this quadratic equation? Is it factorizable? Correct. It is factorizable. Alright? I can actually get two numbers which are factors of 2. And if I add, I would get what? 3. This requires a good knowledge of multiplication table. You know that, right? Good. The numbers are 1 and 2. If I multiply 1 and 2, I would get plus 2. And if I add 1 plus 2, I would get plus 3. So we could say that factors, the factors here, factors are plus 2 and plus 1. So what do? We are going to obtain the root of this equation now. Therefore, n is equal to, and once you get a factor of a quadratic equation, to get the root, to get the zeros of that quadratic equation, all you need to do is change the signs of the factors and divide it by the coefficient of this n squared. The sign of these 2 here is plus. So if you change it, you're going to get minus 2. Divide it by the coefficient here. Coefficient of m squared here is 1. And so minus 2 divided by 1 will still give us what? Minus 2. Do same for that plus 1. Change the sign of that plus 1. You get minus 1. And then divide it by coefficient of m squared here, which is 1. Minus 1 divided by 1 will still give you 1. So these are the roots of this auxiliary equation. Now if you look at this, number 1, this auxiliary equation could be factorized. I use factorization method. It therefore means that the complementary function, the solution to this quadratic equation, even without solving it, will either be that one of y equal to a exponential m1x plus b exponential m2x, or it could be the second solution, which is y equal to a plus bx in bracket exponential mx. Now, whichever of them I chose depends on whether the roots of the equation are equal or not. If you look at this, these roots are not equal. It therefore means that m1 is not equal to m2. We could say that m1 should be equal to minus 2 and m2 should equal to minus 1. Oh yeah, take note, there is no rule that m1 must be the first one and m2 must be this, or that m1 must be the smaller number and m2 must be the bigger number. No rule like that. I could have said that m1 is minus 1 and m2 is minus 2. It still goes. Therefore, the solution that goes becomes y equal to a exponential m1x plus b exponential m2x. And then if you substitute, we could have that our answer will now be y equal to a exponential m1. m1 is minus 2, so you fix that. So it becomes minus 2x plus b, the second constant of integration, exponential m2, I chose minus 1. Minus 1, using to multiply this x, is going to give you minus x. And this becomes the answer to our problem. Answer. That is the solution. That is the complementary function to this differential homogeneous O.D.E. Use this principle to test how far you understand what I've done here on the board by solving this question. In this video, we're not going to take our second question, okay? The question we have it in the board here: obtain the solution of the O.D.E. 9d squared minus 12d plus 4, all in bracket, y equals 0. What does this mean? Alright, this is another form of presenting derivative of a variable. This is the meaning. 9 times second derivative of y, which is the same as 9d2y d squared x. Is that okay? Then minus 12 times first derivative of y. You know this d is raised to 1, so it is first derivative. Is that okay? And then plus 4y equal to 0. I hope you get that. So that's another form in which you can present your derivative term. At the end of my solving this problem, please follow the principle, test your zone of proximal development by obtaining the general solution of this homogeneous O.D.E. problem here on the board, d2y d squared x plus 6dy dx plus 9y equal to 0. Now let us solve this together, okay? So follow along as I handle our problem. We're given 9d squared minus 12d plus 4, all in brackets, and then multiply by y equal to 0. As usual, we're going to bring out the auxiliary equation to this homogeneous O.D.E. The auxiliary equation is given as, okay, so it's going to be 9 times n squared, 9n squared, and then minus 12 times n, 12m plus 4, the constant, equal to 0. Remember, this d squared represents m raised to power 2 in the auxiliary equation. This is d raised to power 1, which is the same as m raised to power 1. There is no derivative term with this constant 4, so no need of putting any m here. Is that okay? Now we shall solve this problem. This auxiliary equation is a quadratic equation, but first let's check, can it factorize or not? Because if we know whether this can factorize, it will really help us to know the particular solution, that is the solution to be looking up to. Are you following? So let's take a look at this. As a principle, you know in solving a quadratic equation, you are meant to use the coefficient of the term bearing square to multiply the constant term. So the quotient here is 9. 9 times 4 is going to give us plus 36 here. Is that okay? 9 times plus 4 is plus 36. So let's check. Are there any two numbers which are factors of 36? If you multiply these two numbers, you get 36. And if you add these two numbers, you would get minus 12, alright, as the summation term. Of course, to think minus 6 we do that for us. Minus 6 we do that for us. So I'm going to write that factors. The factors of this auxiliary equation are minus 6 and minus 6. If you multiply minus 6 by minus 6, you will get plus 36. And if you add minus 6 to minus 6, it will give you minus 12. Having done this, I guess we can now go straight ahead to the value of the root of the equation m. So we're going to have that m is equal to, remember I told you once you get the factors that can solve the problem, simply change their signs, and on changing the signs, divide what you get by what? The coefficient of m squared. Now coming over to this, if you change the sign of this factor from minus, it goes to plus. So this is going to be plus 6 divided by 9, the coefficient of m squared. Or the second factor, which is minus 6, it changes to plus 6 divided by what? 9. You see, at this point, you can actually reduce this You can actually reduce this. You can say that m1 is equal to, or let's simply say that m is equal to 3 divides 6 will give us 2, and 3 divides 9 will give us 3. Or you still have the same here, which is 2 over 3. Did you notice something here, that the roots of the equations are the same? That is 2 over 3, 2 over 3. And remember that we were able to factorize this auxiliary equation, is that so? Therefore, the complementary function that goes for this, it implies that y is equal to a plus bx exponential mx. Remember, when the roots of the equation are real numbers and the roots are equal, that is to say m1 is equal to what? m2. Then the solution that goes to that is this solution. All we need to do is to substitute for our root of the equation, that is m. We're going to have a plus bx and closing bracket times exponential m. Our m is 2 over 3. Just pick one of them, multiplied by x. This is the solution to this homogeneous second order ordinary differential equation. Use this principle, obtain the solution of this homogeneous O.D.E. In this video, we have this next question, alright? We are to find the solution to the D.E. 2y prime prime plus 5y prime plus 6y equal to 0. By the time it would have been done solving this problem, please apply similar principle and test your zone of proximal development. Obtain the solution to the D.E. d squared plus 4d plus 9 in brackets times y equal to 0. For this problem, our homogeneous O.D.E. is giving us 2y prime prime plus 5y prime plus 6y equal to 0. The auxiliary equation to this homogeneous O.D.E. is given by what we have here on the board. Auxiliary equation is, so it becomes 2 times m squared plus, the equation here is 5, so it's going to be 5m plus the constant 6 equal to 0. Now, before we proceed in solving this problem, we need to check whether this quadratic equation can be factorized or not. Because it is important, because if this auxiliary equation, which is a quadratic equation, can factorize, then even before solving, we would know what the solution likely would be. It means we'll be thinking of either y equal to a exponential m1x plus b exponential m2x. Or we'll be thinking of y equal to a plus bx and closing bracket times exponential mx. That is, if this can be factorized. Because if we can factorize, then we know that it's going to produce real numbers as the root of the equation. So the point now is factorize and select from any one of the two solutions, depending on whether the roots of the equation are equal or not. Is that okay? However, if this auxiliary equation cannot factorize, then it means we'll now be thinking of the other third solution, y equal to exponential alpha x, open bracket, a cos beta x plus b sine beta x. So you see why it's important to actually check whether your quadratic equation, the auxiliary equation, can actually factorize. Now looking at this, to check whether I can factorize, first use the equation of m squared here to multiply this plus 6, the constant term, you get plus 12. Then ask yourself, are there any two numbers which are factors of plus 12? If you add these two factors of plus 12 to get plus 5, the coefficient of n, do we have any two such number? I don't think so. There are no two numbers that are factors of 12 which you would add to get plus 5. Therefore, this auxiliary equation cannot factorize. We're going to smile because we have already eliminated the first two types of solution, which we saw at the outset of this topic. I hope you're following. Therefore, I will solve this problem either using complete the square method or using the quadratic formula, also known as the almighty formula. But I really prefer solving using the complete the square method because there is something faster I'm going to teach you and how to quickly obtain the root of this equation, because it's going to be an imaginary root. We know that. Let's handle it and see. How do we proceed by completing the square method? The first thing is to take this plus 6 to the right hand side. Once you move plus 6 to the right hand side, you now divide through by the coefficient of m squared, which is 2 here. Are you ready? So I'm going to divide simultaneously as I move this minus 6 to the right hand side. Are you ready? Let's go. divide this n squared by this 2m squared by 2, and then you'll be left with n squared plus 5n divided by 2. You have 5 over 2n. Then this plus 6 has got over here already, so it is minus 6 here. Divide that minus 6 by 2, you are going to get what? Minus 3. Is that not so? Alright, okay. Having done this, the next step in completing the square method is to find 1/2 the coefficient of this n. And the coefficient is what? 5 over 2. Find 1/2 of it. 1/2 of 5 over 2 is going to give us something like, okay, let me do that. 1/2 of 5 over 2. If you do that, you get 5 over 4. Are you following? You get 5 over 4. So 5 over 4 is 1 over 2 times 5 over 2. That is the half of 5 over 2. Are you following, right? Now, what do you do with this 1/2, the coefficient of n? What do we do with it? So this 5 over 4, we are going to square it. Add it to the left-hand side and add it to the right-hand side. But when you are adding to the left-hand side, you want to take note of something. If you add it to the left-hand side, the next thing is to combine this 5 over 4 with this n and square it together. So why not I do it straight ahead? Must I write this term n squared plus 5 over 2n, then plus 5 all over 4 all raised to power 2? If it's an objective case, of course, no need of doing that. Because you know, after that, the next thing you need to do is to combine this 5 over 4 with this n and then enclose both of them in bracket with square outside. And that's what I'm going to do. So it implies that this is n plus 5 over 4. Then in bracket, I will square it. And that will be equal to, take note, we said you are to square 1/2 the coefficient of n, which is 5 over 2. 1/2 of it is 5 over 4. Then square and add to the left and to the what? Right. So that's going to be equal to minus 3. I'm going to add 5 over 4 squared to it. I hope you get the point, right? If you expand this term now, you are going to get this whole term. So that is the principle. Now we move on. This is now going to give us n plus 5 over 4, then all squared equal to, we'll simplify this. Okay, do that just in one step straight on. This is minus 3. This is going to give you 25 over 16 because it's 5 squared over 4 squared, 25 over 16. Then you work out the LCM. Are you following, right? Take note, I'm telling you that at this point, what you have is minus 3 plus 25 over 16. So, work out the LCM of this is going to be 16 times minus 3, add it to 25. And 16 times minus 3 is going to give us minus 48. Minus 48 added to plus 25. It's going to give us about minus 23. Minus 23. So, this whole term is minus 23 all over 16. What do you do from here? Take the square root of both sides, but it is actually a waste of time if it is objective situation you consider. It's a waste of time going to take square root of both sides here. And of course, I wouldn't take square root because I told you I want to show you how to teach you something very, very significant when you handle a problem like this. Watch. At this point, I am going to get my alpha. Alpha is gotten from this 1/2, the coefficient of m squared that you added to this m. Are you following, right? So this is alpha. All I need to do is to change the sign of this plus 5 over 4. If you change the sign of 5 over 4, you're going to get what? Minus 5 over 4. Then beta will be obtained from here. This part will give us beta. Alright? This part will give us beta. Change the sign as well too. And then take the square root of whatever you have here. Are you getting me? So beta is going to be square root of 23 over 16, which of course is going to give us square root of 23 divided by 4. 23 is not a perfect square, so you have the square root there. 16 is a perfect square, which if you find its square root, you get 4. So you see, we've gotten our alpha and our what? Beta. And so we go straight ahead and select the general solution to homogeneous O.D.E that will solve this problem. Of course, this was solved by completing the square method. I said you can also use what? The quadratic formula. Why not try that out just at the spare time and compare the results? From here, the general solution will now become y equal to exponential alpha x, open bracket, a cos beta x, then plus b sine beta x. Therefore, the final answer to this is y equal to exponential, our alpha is minus 5 over 4. open brackets, the constant of integration, which is a cos beta x. Our beta is square root of 23 all over 4x, then plus b sine beta x. And beta is root 23 over 4 multiplied by x. This, of course, becomes the solution to this differential equation, homogeneous solid. This is the general solution. Use this principle and solve this problem. Test your zone of proximal development. Of course, you can use any of the method you wish. You can use the completing of square method by solving it fully. If you don't want to go through this technique I applied here, or you can choose to use the quadratic formula.